All right, hello again, class. So in this quick video, what I'm going to do is introduce some of the theory and ideas around some of those important decisions and behaviors that insects and other animals perform focused around foraging. So how insects and other animals, again, go about gathering food from their environment. So why is that an interesting challenge? So if we think like a bee, now you've been watching some bees for the pollinator observation in class, they actually have to solve a pretty interesting challenge, and that is how to best get food out of this complicated grocery store that is their environment. So if you imagine, say, a prairie in Wisconsin and you're a bumblebee, you're looking at this diverse field of flowers, and in that environment, the flowers might vary in the sort of value of food that they provide. So if you think about nectar, what's the concentration of, say, sugar in that nectar? But those resources might also vary in their abundance. So say the total number of flowers between species might vary, and also they vary in their distribution. So, there's not all just a nice even carpet of food. That can have really patchy distributions within the environment. So given all that, it's actually kind of a complicated question thinking about, okay, what's the most efficient and effective way to move through that environment and try and gather resources from it? Actually, not a trivial problem. So one body of theory and sort of set of predictions we can make really comes from a simple starting point, and this is called optimal foraging theory. And optimal foraging theory really starts again from this idea that probably what animals are doing is trying to be as efficient as possible. And they're probably trying to be as efficient as possible, especially with maximizing their rate of energy intake. So what's the maximum food per unit time and really energy resources per unit time that an animal can bring in? So if they're going to do that, which sounds like a great thing to optimize, what kind of strategies or approaches might emerge from that? One sort of set of models around this you can think about, okay, if you're foraging on a resource or a flower that is, say, patchily distributed. So there are sort of chunks of bits of flowers or, say, individual plants distributed through the environment, but you have to spend some time searching for those. So one way we can think about, what's the actual amount of energy per unit time that an animal is going to get in that environment? Well, there's really a couple things that play into that. So one thing you can think about is the transit time. So here on this graph on the left, you can see marked out essentially where the amount of time that the insect is going to take to actually find a new food patch, right? So during that time, they're not accumulating any resources. They're just actually having to go forage for a new food patch. Then they find a food patch and they start gaining resources, right? So on the y-axis in this graph, you see cumulative resource intake. So this is an increase in the food they're getting. So they find food, great, and they start gaining some food. But also those resources will start to deplete, and so they might sort of asymptote out. You can imagine that, you find a great plant, you might forage on those quickly, but then each individual flower might sort of slowly start losing, or it's harder to find food within that patch, right? So you have kind of a diminishing returns within that patch. So one of the interesting predictions here is, okay, how long should an animal spend sitting in a single patch, whether or not that's a sort of flower cluster, or can be any other food resource for an insect. How long should an insect spend actually handling or trying to get food from that resource? And if we're thinking from that optimal foraging theory prediction, right, where we talk about maybe the animal wants to maximize the energy intake per unit time, it turns out the best way to do that is to find the tangent between your starting time. So if you think to the beginning of your transit time, start that as your beginning point, and then think about what is the line that sort of touches at its highest point your resource accumulation curve within the patch, right? So here you can see this is kind of the tangent touching the resource accumulation curve. That point is essentially the point where you get the highest slope on this resources per time curve, right? So that's the curve where we predict they get maximum intake of resources per unit time. So we can make a prediction that there's this intermediate time they should spend. They shouldn't spend all of their time trying to get every last bit of resources out, but they also shouldn't leave too early. So in general, we call this body of theory the marginal value theorem. So when you can maybe think of this as, at what point does it stop being more useful to continue foraging within a patch versus moving into it? And what we think this is affected by in turn is actually search time. So, for example, how hard is it? How long is that period where you have to search for food might affect this. And then some of the other key parameters are what's the patch quality? So how fast do you accumulate resources within a patch, or how quickly do they diminish? And some interesting predictions arise from this. So for one thing, you can imagine environments, let's say each patch has the same value, but it is harder or easier to find those patches, right? So this might show up as long transit times between patches. So it takes a long time to find your next patch, or a very short period. So hard to find patches would be in the blue line here, and then easy to find, say, close together patches are in the red line, so transit times are shorter. It turns out even if the patch value is the same, you end up getting different predictions when you draw that tangent line. So in general, when resources are sort of harder to find or it takes a longer to go get them, animals should actually spend longer within a patch to maximize the rate of food intake. But if resources are easy to find, if your next patch comes quickly and easily, you shouldn't actually worry about getting every sort of last drop out of the patch that you're in. So do these patterns actually hold in real life? Some of the best direct empirical tests of this are actually from vertebrate systems. So this is an example from kind of an honorary insect from the animal world, but a chipmunk, but where they experimentally manipulated the distance to food for these chipmunks. And indeed, they find that as you take longer to actually find the food, so longer travel time, the time in each patch increases, and also the total amount of food that they collect increases. So consistent with our predictions from that optimal foraging theory. So at least some animals are following these rules. And of course, these kinds of, broadly thinking about optimal foraging theory, this strong selection interest in trying to maximize resource intake per time, this really underlies also, for example, the patterns you saw in the last video of this is a bumblebee optimizing her foraging route. And this remarkable ability, we think, is really directly driven by this desire for optimal foraging, right? So by minimizing travel time, what they're doing is, really minimizing the costs associated with travel, and therefore maximizing the sort of rate of energy intake.